is a podcast that explores our relationship with the natural world. It consists of interviews, stories, and discussions that highlight the notion that nature is not a place one goes to, but rather a place one is already a part of, that we are nature. For those of you who are new to the podcast, my name is Stefan Van Noorden. On this episode of Nature Revisited, we are pleased to welcome Marcia Bjornerud, author of the new book Turning to Stone, to the podcast. Marcia Bjornerud is a structural geologist and writer whose work has focused on mountain building and earthquakes. Marcia is a Walter Schober Professor of Environmental Studies and Professor of Geosciences at Lawrence University in Wisconsin. Marcia is also the author of several books, including Reading the Rocks, Timefulness, and Geopedia. Her latest book, Turning to Stone, The Subtle Wisdom of Rocks, is part memoir, part geo-reminder, and part love letter to rocks. Marcia sketches together the story of how her relationship to rocks helped her to better understand what it means to be an earthling. At a time of subatomic colliders and space telescopes peering into the beginning of time, Marcia celebrates stones as a way of anchoring ourselves to our planetary inheritance and bringing reassurance in a time when our human systems are showing signs of fragility. Marcia joins me from her home in Appleton, Wisconsin, to talk about turning to stone. Marcia, welcome to Nature Revisited. It's a pleasure having you on the podcast.
It's a pleasure to be with you, Stefan.
So let's go back to the beginning. What are some of your earliest memories of rocks? And when did you first start to sense that you had a special connection with them?
Well, I grew up in western Wisconsin, out in the woods. And I think like many children who grow up in the countryside, I developed an early relationship with the landscape. I sensed that there was animacy in the landscape and that different components of nature had personalities. In the wintertime, being fascinated by great icicles that would grow out of the sandstone banks of our creek that indicated that the rocks were transmitting water and responding to the weather in the same way that all the living parts of the landscape did as well. Another early memory is looking for agates and other types of rocks in a gravel pit that was near our house that I would learn much later was a memory of great meltwater rivers emanating from the edges of ice sheets late in the Ice Age, and puzzling over the diversity of the rocks and sensing that each one of them had some kind of story to tell, but not quite being able to read their texts at the time. But I think I had an early inkling that there were hidden messages in rocks and in the landscape itself that one could learn to read.
So when did you first decide that you wanted to be a geologist, and why?
I do remember quite vividly in the first or second grade seeing a film about the birth of the island called Surtsey off the coast of Iceland in the 1960s. It was a black and white film, and there were spires of steam and ash coming out of the North Atlantic that suggested that there was this throbbing of the earth somehow concealed beneath the cold Atlantic waters. And I hold that memory keenly in my mind. I don't recall anyone ever saying there's a field that's called geology, that people study this kind of thing. Our school, like most in this country, really doesn't offer rigorous earth science. So it was really only as the first year student in college, I happened to take an introductory geology course for the lab science requirement. Almost immediately, I was hooked. I think the thing that really attracted me was the vast explanatory power of geology. I had always been interested in word origins, etymologies, and I saw that geology was in some sense the etymology of the whole world. It explained how things came to be the way they are now. To me, that was irresistible.
So, how would you describe and define geology?
Contrary to what I think many people would say, it's more than the study of rocks and minerals, although those is a text. To me, it's really a way of seeing, and in particular, capacity to imagine other versions of the world, to see in 4 dimensions, including time. I realize more and more that that's the really challenging conceptual content that we need to convey, the cognitive habits that allow us to move freely across vast spatial scales and temporal or time scales in our mind's eye, and hold all of these versions of the world simultaneously in our minds. So it's a way of seeing and envisioning more than anything else.
Can you describe how your relationship with rocks, as you say, became so very personal that rocks have taken control of my life?
It's largely from spending so much time in their company, and in particular in very remote places. I've been lucky to work in the high Arctic regions of Norway and Canada, where the human imprint is so minimal that there's just no question that nature's in charge. The gravitas of the rock is so clear. For I think in these places in particular, one's own consciousness becomes subsumed in the larger logic of the landscape. It's just a fact that as a geologist, the places I've lived, the people I've encountered, have largely been dictated by the rocks that I've been obsessed with at any given time. I'm grateful to the rocks for introducing me to people from all over the world, allowing me to have some remarkable adventures with other human beings.
You say in the book that you have come to understand that stones and rocks have language, tell stories, and even have personalities. Can you share some examples of that and how you became able to understand them?
And in some ways, I've come full circle back to my childhood, feeling that in some way there are sentient beings among us in nature. What I mean by personalities is that different rock types, whether they're sediments deposited at the Earth's surface recently or long ago, they've had such different life experiences that inevitably they do have different characteristics and different stories to share with us. They do have different personalities. Some rocks are easily read, and others are a little cryptic and need a bit more patience if we were to decipher what they're saying. So I really do have rather different relationships with different rock that I encounter. I can even feel frustrated with rocks that are so mute and hermetically sealed that I can't understand them at all. It doesn't make sense scientifically, and yet I think many geologists, if you talk to them, would agree. They have a relationship with rocks, even unrequited love for different rocks.
So your book is a journey through earlier worlds, with each chapter representing a different rock. Is there a rock that fascinates you more than others, and why?
If I had to identify just one, it would probably be a rock that has a terrible name, pseudotacholites. And this rock is a glassy rock that is formed by frictional melting in an ancient earthquake. And it's found usually in rocks that were at one time deep in the subsurface, many kilometers down, and have now been brought up to the surface or ruined by erosion. And the reason they're so fascinating is that they are really the only direct glimpse that we can get of what happens on a fault during an earthquake. They're rocks that have formed in seconds in an ancient seismic event. So I'm fascinated by these rocks that have a story to tell us that we can only sense today at the surface. We can't actually see what happens on a fault zone at depth when an earthquake happens today. The cacolites are our one window into the actual physical mechanisms that happen during a great earthquake. That's one example of a rock that has lured me and my kids with me around the world.
So can we highlight the importance of a few of the other rocks on your journey, starting with basalt?
Basalt is the most common rock type at the surface of the Earth, and in fact, probably the most common rock type on all of the rocky planets and moons in the inner solar system. I use that rock in the book as a kind of entry point into my development as a geologist. That particular chapter is about my college days, trying to learn the language of rocks. Even a rock that's so common can have many different guises depending on its post-eruptive history, whether it's interacted with water or how it's been changed by weathering and exposure. Basalt is easy to make. Most planets and moons in our inner solar system has learned to make basalt. I use basalt as an entry point for people who maybe haven't had an experience to get to know many rocks.
How about turbidite, the Arctic, and Ellesmere Island?
Yeah, so this is a rock type that probably most people haven't ever heard of. It's a sedimentary rock, and as its name suggests, turbidite, it has something to do with turbulence. And it's a fascinating rock to me from both a scientific and a history of science perspective. This is a rock that is sandstone grading into finer, even shale-like rock in repetitive sequences. And it was known starting probably in the 1700s and 1800s in most great mountain belts around the world. But no one could really explain how these rocks formed. Their characteristic signature is this very repetitive sandstone to shale sequence. This is a frustration to early geologists because one of our primary principles is that the present is the key to the past. We look at things that are happening on the Earth today for insight into how sedimentary rocks could have formed in the past. And it was only sort of by accident when there was an earthquake off the coast of Newfoundland, and in rapid succession, telegraph cables that had relatively recently been laid on the seafloor, something had snapped the cables in succession. And this is the beginning of the discovery of the phenomenon we now call turbidity current, which are slurries of sand and water, dense kind of muddy mixtures that come careening off the continental shelf out onto the deep seafloor, and over time are the thing that lay down these strange rocks that we call turbidites. My own experience with turbidites, my main one, was an entire summer spent up in Ellesmere Island in high Arctic Canada. Mapping these very repetitive rocks was a challenging way to spend a summer long ago. But now when I meet turbidites in other places, I feel like they're old friends. I understand them, I know their origins, and they speak to me.
And then there is granite, a new geology department, and personal stress.
Granite, for me, means a lot of different things. Granite is really a unique invention of Earth. The moon, for example, or Mars, or Venus. We don't think that those planets have ever managed to distill granite out of their interiors. So granite's an igneous rock, like basalt, but it's not obvious how the Earth has managed to create so much granite. The mantle from which all rocks ultimately come is decidedly not at all granitic. Granite has much higher concentrations of potassium and aluminum, calcium, sodium, and some of these other light elements that are in the mantle, but are in relatively low concentrations. So somehow Earth has managed to sort of scavenge lots of these lighter elements out of a mantle that is low in those elements. And our current understanding is that the bulk of the continental crust is broadly granitic. And that's an important distinction at the planetary scale, because basalt, being one step away from the mantle, can sink back into the mantle from which it came in the process we call subduction. The basaltic ocean crust has a kind of short lifespan of only about 150 or 170 million years before it goes back into the mantle. Whereas granite, once it's formed, is very resistant to being recycled because it's got a lot lower density with all those lighter elements in it. It's really hard to get rid of granitic continental crust. So granite is the foundation on which all of us live. Earth is the granite planet in contrast to our near neighbors in space. In the book, I use granite as a kind of metaphor for stability, which it is. There are also just fascinating history of science stories to be told when we talk about granite. As I said, it was not obvious how Earth could create so much granite. As late as the 1950s, incredibly enough, there were geologists, quite a few of them, who were arguing that granite was not even an igneous rock, that it was not created from magma, but was in fact a strange kind of modified sedimentary rock. The theory that is now kind of an embarrassment in geology called granitization. It was an attempt to answer this question: where does all this granite come from in a way that we now consider exceptionally strange fact that Earth has so much of this rock type that is not easily explained. Granite is a very common and familiar rock, but it too has so many stories to tell, both scientific and human.
So can you describe the relationship between rocks and water? And how important is it?
Hard to imagine Earth without water. Almost every geological phenomenon on Earth would be different in the absence of water. Seafloor basalt, 150, 170 million years old, is cold and dense enough to sink back into the mantle at subduction zones. Above those subduction zones in places like Japan and Indonesia, the Aleutian Islands, the North Island of New Zealand, the Philippines, these are all subduction zones where cold, basaltic ocean crust is descending back into the mantle. Above those subduction zones, in every case, there are volcanoes, even though cold rock is being pushed back down into the mantle. The reason that we have melting at all in those settings, and in most of those settings we have big, bad, explosive volcanoes like Krakatoa, is water. As that ocean slab is going back down into the mantle, from the moment it was born, flushed with water, and as it descends down into the mantle, it's carrying water at a depth of something like 50 kilometers, which would be about 30 miles. It starts getting hot enough, that slab, it's still cold, but it's heating up, and it lets go of that water. And the water acts to lower the melting temperature of the overlying mantle that's just above that slab. We say that the water is a flux. It's kind of like steel making. They add carbon and other things to lower the melting temperature of iron, or in glass making, you add sodium to lower the temperature of the silica. The water lowers the melting temperature of the Earth's mantle, giving rise to volcanoes. And that process actually is linked with the creation over time of granitic continents. Probably if we didn't have water, we wouldn't have granite, we wouldn't have continents. Earthquakes would be completely different too. Water is implicated in many earthquakes. And in fact, we can actually cause earthquakes by pumping fluids related to fracking, for example. In understanding of earthquakes, we're understanding more and more. In many cases, it's deep, poor water that is responsible ultimately for triggering earthquakes. We probably would not have nearly as many mineral species on Earth if we didn't have water. We can look at the moon. We have moon rocks. So far, I think something on the order of maybe 300 or 50 minerals have been identified from the moon rocks, which is a tiny number compared with the 6,000 or 7,000 minerals that we have on Earth, many of which only form in the presence of water. You would have a much impoverished inventory of rocks and minerals on Earth without water. And then another thought that occurs to me is just the remarkable fact that the internal process, the tectonics, which are really driven by the heat energy of the interior of the Earth, are about matched with the external processes of erosion, which is water running over the landscape and slowly wearing mountains down. And it's really a remarkable fact that over time, the rate of mountain building is about matched by those processes of erosion. No mountain exists forever. Eventually, water has the upper hand. The dynamism of the surface of the Earth reflects not only the tectonics, but also the very energetic activity of eroding water. It would be such a radically different planet. Almost everything about the Earth would be different in the absence of water.
So how do rocks help us better understand our place on the landscape?
My hope in writing books about rocks is to remind people that we are fundamentally earthlings. The Earth is not just a passive backdrop to our lives. It defines everything about our existence. And I hope to share this geological worldview of being able to see back through time, seeing in the mind's eye multiple versions of landscapes, which to me doesn't diminish my experience of being a human. It enhances my sense of being an earthling, that I'm part of this great continuum. Things do change, but that's okay. That's the way this planet has maintained its vibrancy and its vitality for so long. Continuity, that's the better message. Not that we are insignificant in the long history of the Earth, but that we are inheritors of this amazingly long-lived, creative, resilient place. And rocks tell us this. They're full of memories of earlier ecosystems, cataclysms, and recovery. I'm trying as a writer and scientist to share that worldview and offer people a portal into this different view of landscapes and rocks.
So everything in the universe evolves. How has geology evolved, and how do you see its future?
Well, geology really has evolved, especially in the last few decades. And I feel lucky to have been in this field during the time of its flowering into a very rigorous science. When I was an undergraduate, incredibly enough, the theory of plate tectonics was really only about a decade old. It's almost embarrassing to acknowledge that we didn't know how the solid Earth worked until the mid-1960s. We didn't really have any good grasp how climates of the past had changed and why they had changed until the late 70s or early 80s. A new paradigm that has emerged again since I was in graduate school would be the whole field of biogeochemical cycles, the intimate interrelationships between the solid Earth, hydrosphere, the water cycle, the atmosphere, and the biosphere. How elements and compounds are constantly traded among all of these entities over vastly different timescales. Only in the last few decades have we developed these conceptual frameworks that are allowing us to get some understanding how the Earth system as a whole works. and how complexly interconnected the solid Earth is. I see geology continuing to grow in depth and nuanced understanding as computational capacity grows, that we really do need big computers to be able to find patterns in. Sadly, however, counteracting the potential that the field has are, of course, recent cuts to people's funding and also the closure of a lot of geoscience departments, sadly, in the US at many campuses based on the misguided thinking that somehow we don't need earth science anymore. And I would argue that earth science is the one field that all earthlings absolutely do need on a planet that is being stressed by human activities in a time when we need to be addressing the realities of climate change. We urgently need more earth scientists and informed earth citizens who can elect and become politicians and policymakers who can guide us an uncertain future.
How does the Baraboo Range in Wisconsin reveal the sacred and the ritual of recreation that suggests that rocks really are in charge?
They are in charge, absolutely. The Baraboo Range is famous, at least in the Midwest, because it's this ancient, buried, and now being unburied mountain range in southern Wisconsin. It's a mecca for field trips from all around the Great Plains and Upper Great Lakes region because it does preserve a memory of reincarnation. So the rocks of the Baraboo Range, the Baraboo quartzite, were originally laid down about probably a 1.6 billion years ago or so, tropical climate that left a very pure sheet of beautiful quartz sand laid down by rivers that at that time were not channelized. They were just braided systems running across the landscape, and laid down the sheet of beautiful quartz sand that then got wrapped up in an ancient mountain building event and changed to a beautiful pinkish purple rock we call quartzite. The beauty of this rock and its whipple mark, they receive the memory of a river running across the landscape. The Baraboo Hills are this amazing story of the cyclicity of sedimentation, mountain building, erosion, new sedimentation. For myself, I remember going as an undergraduate on a field trip to the Baraboo Range, and now I've been back with my own students many, many times in an almost ritual of veneration for these rocks that also record geological rituals.
So finally, what is some of the wisdom that you have learned from the study of rocks that you feel could be applied to our current environmental crisis?
To me, there is so much wisdom in the rock record. If we humans could only be quiet for a second and learn to listen. Some of the lessons would be certainly deep recycling, seriously retooling our entire economic system to ensure that everything can be reused. We shouldn't have gigantic landfills. We've got to learn from the earth how to recycle, how to build things that are modular, reparable, reusable in a deep way, and somehow fix our economic system to align with the way the earth works. I do take comfort in this time of environmental crisis at looking at the record of past cataclysms, mass extinction events. There never has been a time since life first emerged at least 3.8 billion years ago when life has completely been extinguished. That is the source of some existential comfort to me. We can make the quality of life pretty bad for ourselves and a lot of other organisms, But I think Earth and life in the end will be okay. I think more than anything, the study of rocks instills a sense of humility that our version of the world is not the only one. There'll be others in the future. And getting a proper sense of proportion about our time is the main lesson to me. There's so much natural intelligence out there as opposed to the artificial kind that everybody's so preoccupied with these days. If they can just tune into it, you'll all be so much better off.
I hope you enjoyed this conversation with Marcia Bjornerud, and that you take the opportunity to read her latest book, Turning to Stone, as well as her other books, Reading the Rocks, Timefulness, and Geopedia. If you enjoyed this episode of Nature Revisited, please share with friends, family, and colleagues. And please rate us on your favorite podcast server. It will help us to reach a larger audience. You can follow Nature Revisited on Facebook, Instagram, YouTube, and on our website, nordenproductions.com. And please share your comments and suggestions for future guests for Nature Revisited on the comment section of this episode on our website. The music for this episode is The Machine in the Garden by Ben Cosgrove from his album, The Trouble with Wilderness. The Nature Revisited team consists of Stefan Van Orden, Charles Gagan, and Scott Chasky. And I hope you will join us for the next edition of Nature Revisited. And in the meantime, remember, we are nature.